Oh shit. You alright there, phone? You're a little drunk? Okay. Alright, let's take a look here. So what's the new thing I added in? Anybody see? Oh my god, I got a freaking mind. Okay. So I'm going to give you a decent way to do it. See if what you guys think about it. And I forgot to put something. Okay, we'll get there. So what is the amplitude? That's crazy sauce. And then if I factor the inside, how do I do that? Yeah, I can take a pi over 2 out. And what am I left with? X plus 1. That was nice. Thank you, Jeff. Okay. What's K? K? Yeah, K is always the multiplier of the X. You can almost think of it as if it was just that, it would be the slope. Or if you don't want to think about it, it's just whatever number's in front of X. Right? So I knew that from the beginning. I can see pi over 2. So take a minute and figure out what the new period is. Don't say anything. This always trips people up. So if I ever have fractions, I'm going to do 2 pi divided by k. How do I divide fractions? Yeah, multiply by the reciprocal, yeah? And then what happens? The pi's, it's very sad. I want the pi's to cancel. I ended up with what? 4. Holy shit. Okay. Which makes the step size really, really nice. Why do I divide by 4? Is this 4 steps? Give me 4 steps? Yes. So 4 over 4 is 1. Okay. How much do I phase shift by? 1 to the left. Now, real quick, I want to point this out. I ask you for the phase shift, but we don't really apply it directly. Because it's trig functions, I can kind of look at them a little differently. I can do this kind of stuff. I can figure out the step size. I kind of incorporate the phase shift in the work I'm doing. I don't graph something and then move everything back 1 the way we did before. Because trig functions have kind of a lot going on. So, not sure if you guys are really with me. So I want you to identify this, but we don't really apply it like we did in the past. It just kind of happens in the work that we do. What's the vertical shift? Downward. Because of this guy. So that's the new part. Which means, where will the midline be? That's what I forgot to put in here. Where will the new midline be? Normally it's at the x-axis. It's at y equals 0. Where will it be now? Y equal -1. So this is gonna oscillate around y equals -1. So I'm going to show you a way to do this to incorporate it all in one, or you can graph this like we did yesterday and then shift all your points down 1. Completely up to you. Let me stop for a minute. Understandably, students hate this because how many parts are there to this? A few, right? But again, none of what we just did is different from any transformations we've done before. They're all the same transformations. There's just a lot of them. This thing, again, this thing. Why did I make this equal to 0? And what is this? And what's this here? Where'd that come from? Will it always be this? What is this from? It's what's inside cosine, yes? I really want this to make nothing but sense. I know, this is unnecessary. You don't need this to graph it. It's just really nice to have something tell you where to start, where to end. It's just really nice to have that. I need you to get what I'm saying. When does cosine start? When x is, where we consider it to start?
0.
When x is 0, and where is it at x equals 0? 1. So when the inside of cosine is 0, that's where it starts. I need this to make nothing but sense. For a normal cosine function, don't we start at 0, then cosine of 0 is 1. So when the inside is 0, it begins. When does it end? When does it end? What's the period of cosine? 2 pi. So if it starts at 0, it's going to end at 2 pi. So when the inside is 2 pi, that's when it's going to end. Mathematically, if I solve those, if I start undoing the shit to x, I'm kind of applying the transformations to 0 to 2 pi. So it's going to go and then it's going to end up where it's supposed to be. Okay. So I'll point out how this is not necessary after we do it. But again, it's not that I'm making you do extra shit. You can do this or not. But I'm telling you, this is so freaking nice to have. How do I solve this? Subtract pi over 2. And then divide by pi over 2. I don't even care that it's fractions and fractions because they just cancel and I'm left with x equal to -1. Dadgummit, got an extra little thing. Okay. So now I'm going to start at -1. Why does that make sense? Because I used to start at 0, and what was the phase shift? What was the phase shift? Left 1. So that matches up. Do you already see how this is not necessary, but it's just nice to verify other shit? I need you to see this. Okay, so you do not have to do this. But my God, if I were you, I'd do it. Just so I can make sure everything's kind of coming out right. How do I solve this thing? Let me show you a little secret. Not secret. Do you guys see something that's in everything? There's no 2 in them. These don't have a 2 in them. You guys okay with that? You guys understand that I didn't forget my meds this morning? These both have a 1/2 in them. But everything has a pi in it, yes? So can't I just cancel pi? I could divide everything by pi. Even if you didn't see that, you could still do it, but it's a little easier now. Now what do I do? Subtract 1/2. What's 2 minus 1/2? What's 2? Is it 2 4/2? So 4/2 minus 1/2 is 3/2. Can you guys just see what the answer is there? Half of what is 3/2? 3. You guys see that? Sometimes you could just step outside of an equation and go, what's freaking 3? If you double both sides, you get x equals 3. Okay. Maybe. Okay, and why does this make sense? How long does it take for it to go through a cycle according to this work? 4. And what was that period? All right, do you start to see what I mean? I'm recovering stuff I already knew in a different way. This is very direct, though. It says start at -1, end at 3. So when I go to graph, it's kind of easier to look at this than it is to figure out what all this is trying to say. But this kind of verifies what I've done. So I start at -1, and then how big is each step I take? 1. And I know I stop at 3, which is 4 steps later. Now here's the trick. Not the trick. I'm going to apply the downshift at the beginning. So where's my new midline now? We already said this. Yeah, so at -1, I'm going to put a little, it's not an asymptote, but it's just kind of like my midline. You with me? Usually it's the x-axis. Now it's not, so I just want to give myself a little something visual to look at. Let's see if you guys are cool with this. How far away from this midline do I go in either direction? What tells me that? Amplitude. So if I go 2 up, I'm at 1 now. And if I go 2 down, where will I be? -3. So now my function is going to live within here. Do you guys see that? Okay. All right, let me see if you guys are really with me. So what function do we have? Cosine. And I'm starting at -1, correct? And where does cosine start? At its maximum. Then it goes, let me see if you guys are really cool with this or not. Then it goes where? It goes to the midline, correct? Starts at the high, goes to 0, but it's the midline. Then it goes low. Then it goes midline. Then it goes high. My scale's a little off, but I'm okay with that. So I really want this to make sense. If I have a normal cosine, doesn't it start at 1? Then it goes to 0, the midline. Then it goes 1 below the midline, and so forth. So everything's based on the midline. If the midline moves, now my cosine starts at the maximum, goes to the midline, which is like 0, goes to the minimum, goes to the midline, goes to the maximum. That's what it always does, which is why it's powerful to figure out the step size, because that's exactly where the next thing's going to happen, the next beat. Maybe. I love you guys. Okay, and now I just got to... Okay, and that's perfect. The book, I think, sometimes says do 2 cycles. You don't have to do 2 cycles. This is dumb. It would just be... And then I got to make a larger freaking graph. It doesn't matter. I'm just going to, this picture is going to repeat forever in both directions. So all I really need is 1 cycle. If I kept going, where would I stop? If I did 1 more cycle, where would I stop? 7, because the period's 4. It would take another 4 for another cycle, another 4 for another cycle. Okay. But don't. So you guys try this side. Go for it. I'll leave this up here, so it's... Oh, sorry. You need this, and you need this. You need this. You didn't get one of these, right?
Is that from yesterday or today?
That's today.
Oh, no, I continue. Thank you.
Oh, did you? I thought you got... Wait, what?
No, and I need the one from yesterday too. If you guys did one.
Oh, you need this one?
Yeah.
Oh, did I give you the practice test?
No.
No. And then you need... oh, I got you. Let's see, where would it be? Here it is. Sure. I'll put in here midline. love these problems, Jeff. Just to remind you, be really careful when you're factoring. When you take something out, you're dividing it out. So you can think of it as, so I'm dividing by 2, correct? And dividing by 2 is multiplying by, there you go. So if you take a 2 out, you multiply everything by 1/2 to see what's left inside. Feel free to compare answers to people near you if you want to. If you don't trust those people, then don't. Oh, this is the rest. You need that little lady from Poltergeist or something?
This little thing is clean. Step into the room.
Oh boy. I'm gonna sort of start catching up to you guys a little bit, make sure everything's going okay. So whenever you take a 2 out, you can think of it as multiplying everything inside by 1/2. If you take a 2 out, aren't you cutting everything in 1/2 inside? That's all, right? So real quick, so you guys look at me crazy. How do you factor 2x plus 4? What do you take out? 2. What are you left with? 1/2 of 2 and 1/2 of 4. When you take a 2 out, you cut everything in 1/2. You just normally don't have to think of it that way, but if you have fractions in there, it's better to think of it as multiply by 1/2. Makes it easier. Does that look good so far? Keep going. I'll catch up to you a little bit. Yeah, shit. That might be better. That's good. Yeah. next line of stuff.
They're gonna be doing a show with the labyrinth. I thought it would with like the orchestral accompaniment.
Did I know that? At Balboa Park, we're like out.
And they're doing it March 19th, I think. But yeah, it's gonna be, I don't know where. It looks cool though. So it's
Hell
like
yeah.
80 hours.
Hell yeah. I love that shit. I
Yeah.
love when they do like the symphony bands, Star Wars, for example, or something, or when they have like a movie, but they have that. Just makes it cool. I went and watched Princess Bride at the Shell. It was just
Yeah, that's cool.
Yeah.
I love that movie.
How's this? Is everything matching so far? What's the phase shift? Yeah, pi over 4 to the right. And then if you want to, you can take the inside, set it equal to 0. Take the inside, set it equal to 2 pi. Okay, I did that a little fast, but oh well. And what does this match up with? How far apart are these two things? What's 5 pi over 4 minus pi over 4? What's 5 pi over 4 minus pi over 4? Yeah, 4 pi over 4, which is pi, which is what the period's supposed to be. So that makes sense. It takes me pi units to get a full cycle in. Vertical shift? Up 1. So the midline is now at y equal 1, because it's normally y equals 0. I like it. So you guys are all cool with the x-axis is y equals 0, and the y-axis is x equals 0. So good things to know. So now considering I shifted to the right pi over 4, I'm going to kind of make my scale, my graph a little tilted to the right. So I start at pi over 4. What's my step size? Can't beat that shit. It's awesome. So pi over 4, I don't care if you don't reduce. 2 pi over 4, 3 pi over 4, 4 pi over 4 is pi, that's right. 5 pi over 4, that's where I end. What's up, Laura? I don't know if you guys know I can see you sometimes. It's like your faces go. Like there's something. So again, every step I take, every move I make, goes by pi over 4. Every cake you bake. And then of course, my midline is going to be at y equal 1. I'm going to make my scale a little smaller than I normally might. And my amplitude, I still didn't make it small enough, did I? It's too bad for me. My amplitude is 4, so how far up do I go? 5. And how far down do I go? -3. I like that. So if my amplitude is 4, it would normally go from -4 to 4. I moved everything up 1, so now it goes -3 to 5. So now it's going to do all of its oscillations around that dotted line, around that midline. So what kind of function do I have? Sine. It starts at pi over 4. Where does sine start? No, that's cosine. Where does sine start? Sine normally starts at 0, or a better way to say it, starts on the midline. So it's going to start here. Then it goes where? Up to the max, back to the middle, down to the min, back to the middle. That's what sine does. Second? Oh, thank you. I didn't make this long enough. And now you can just fill it in. So you could graph this in the calculator. It's just not going to be very easy to compare because the scale in the calculator is going to be kind of wonky compared to this. But at least you can see it's going to be, you can tell it's up, it's going to over, it's going to graph the whole damn thing. It's not just going to graph one cycle. That's another thing that makes it a little hard to compare to your calculator. What's the function related to sine? There's 6 trig functions, right? So which other function is related to sine directly? Cosecant. Tangent is related to sine and cosine. Cosecant is 1 over sine. Are you guys with me? So listen. This is not the best to do this. I'm not going to do it on this one. This one will get a little weird. So let's do this. Let me give us a fresh thing. So what we're about to do now, we studied the hell out of sine and cosine. And we got 4 other trig functions to worry about. Yeah, so let's do those other ones. Let's talk about trig baby. Let's talk about let's start with let's just do a normal unshifted sine function. Is that a dot? It is. So what I mean by that is just good old sinus. So I'm going to graph a little more than normal. Let's see. I'm going to do kind of a smaller thing here real quick. So what are my main things I want to use? I want 1, 2, 3, 4, right? What are they? What is this one? This is first one. All right, what's this last one? How long does it take sine to go through its whole cycle? 2 pi. So what's in the middle? Cut that in half. Pi. Cut it in half again. 5 or 2. So what's this other one? That's this last 4 little dude? 3 pi. And I'm going to do negative pi over 2 also. And maybe even negative pi. Yeah, we leave those 4 little guys out. It's not fair. So I'm doing this to analyze eventually. We're going to analyze what the shit is this guy. So sine, of course, starts where? It's not been shifted. Where does it start? 0. And then it goes maximum. And if I go the other way, it'll go minimum. Yes? And then it goes back to the thing. So it goes back to the thing back there. And then it goes minimum. And then it goes back. Okay. Yes? So here's what sine would look like. For me, that's not terrible. But it is sort of bad in the middle there. But it'll be okay. Okay. And it would keep going, of course. Yaha! Yoo-hoo! So I'm going to use a different color. So let me ask you. If cosecant is 1 divided by sine, where will cosecant have an issue? Are there any points where cosecant will freak the shit out?
0.
Whenever sine is 0. So 0 is one example. You guys with me? What happens at locations where there's values not the domain of my function? What do I have to put there? A freaking asymptote, a wall. Yes? That's nothing new. It's just this is not a polynomial, but it's the same idea. Does the bottom ever become 0? Hell yeah. Sine becomes 0 at 0, for example, so I better put a wall here. So I'm about to graph cosecant on top of this poor little sine, dude, because I want to show you something. There's going to be another wall here, because that's where sine is 0 also, yes? There's going to be another wall here, and a wall here. Okay. So here's what's really cool. Cosecant is 1 divided by sine, correct? What's the output of sine right here? And what's 1 divided by 1? Holy shit. So then cosecant shares a point with sine right there. Now, real quick. Aren't these decreasing to 0? Why are some people saying no? Aren't the outputs going to 0 back here, yes? Okay. Isn't there a place in the middle here where it's like an output of a half? Do you guys agree with me? Doesn't sine have an output of a half somewhere? What angle makes sine a half? 30 degrees, or pi over 6. I like it. So right in here, there's a place where it goes to a half. What's 1 divided by a half? 2. So I really want this to make sense. 1 divided by anything between 0 and 1 flips and becomes bigger. So wherever there's a place that it's 1/2 output, no, get out of there. Go away, okay. So right here, there's like a 1/2 output, correct? Which means my cosecant is going to have an output of 2 there. Isn't the same thing going to happen over here? Where the output is like 1/2? My picture is really sucky, but oh, too bad for everybody. Won't 1 divided by 1/2 be 2 again? So doesn't this cosecant look like this? It should look, Jeff, do that all again, dude. It should look almost like a parabola in there. Over here, what's 1 divided by -1 right here? There would be -1, correct? And then isn't this stuff getting smaller? But aren't they all negative? Isn't this output negative? Isn't that output negative? And maybe it's -1/2, so 1 divided by that would be -2. So I need you to see what happens. Doesn't it just become another little parabola looking dude going down like that? Every parabola dude going down like that. So how do I graph cosecant? You graph sine, and then you put little cups on the tops and bottoms of the damn hills. I need this to make nothing but sense. So here, just to pick a number. Isn't there an output that's 0.1? Do you agree there's an output right here that's 0.1? Let me make sure you guys can see what I'm talking about. Right there. There's an output that's 0.1, yes? You guys with me? Because it's going to 0. Of course there's somewhere the output is 0.1. What's 1 divided by 0.1? 10. So wouldn't the output of a function that is 1 divided by that, wouldn't that output be frickin' 10? Way the shit up there, yes? So that's why it's doing this. As my sine outputs approach 0, my cosecant's going to frickin' infinity. Or negative infinity if I'm down there. So how do I graph cosecant? I graph sine, and then I just throw cups. Bottom, up above, down below. It's almost too nice to believe. So cosecant is not a whole new graph. No, you just draw little parabolic cup things on top of a sine function. So there's nothing new to learn about cosecant except that. I need you to see what I'm saying. So if I give you a problem, I say graph 2 cosecant of pi x minus pi, you pretend like it's sine, you do a dotted sine graph, and then you just draw cups. So then you're done. Don't forget to put your asymptotes in, yes? You guys at all with me? So how would I do secant? Graph cosine and put freaking cups on top of it. Can somebody give me one location for an asymptote for a secant function? Y pi over 2. There will be an asymptote of pi over 2y. Cosine of pi over 2 is 0. Secant's 1 over cosine. It'll be 1 over 0. It's going to freak out. Got to put a wall there so the poor little dude doesn't go insane. Yes?
For functions that shift up and down, is it just the midline?
Yeah, so I was going to look at this guy. Maybe I can do it now. This one we just did earlier. It wasn't the best one to start with, but this one, if I wanted to graph for cosecants, everything's the same except I would have put cosecant here. I would have done this dotted, and then my last thing would have been put a cup here. The weird thing is this would be an asymptote. Put a cup here, put a cup there, put a cup everywhere. So wherever it hits the midline would be the location of an asymptote. So literally, if I give you a secant or a cosecant thing to graph, you pretend like I said cosine or sine. You graph it, and then you just put the cups. That's all you got to do.
So you want the original function dotted, and then the
Yes.
secant lines.
Yes. Sweet. It's not just for me, it's for you too. It just makes it easier to kind of keep things proportionally right. Okay. So in this one, it would be, there would be an asymptote here, there would be an asymptote here, and I have a cup going there, blah, blah, blah. If I would have asked you secant instead of cosine, I would have done all the same work we did, and then just throw little cups, and I would have made this dotted. Are you guys kind of with me? It makes sense because cosecant is related directly to sine, just with 1 over, which is why there's some asymptotes, because the poor little sine dude becomes 0 sometimes. Freaks cosecant out. Okay. Maybe. So what's the only ones we have left? Tangent and cotangent. Okay. So of course those should be very closely related because they're also reciprocal functions. So let's look at tangent. Let's see if we can do this without making a table. What's tangent of 0? Zero. Because tangent sine over cosine, sine of 0, 0, 0. What's tangent of pi over 4? 1. What's tangent of negative pi over 4? Negative 1, because that's in quadrant 4. They have different signs. Tangent's the ratio of the two, so it's going to come out negative. Can we stop for a minute? So remind me real quick, what's tangent again? What over what? Sine over cosine. So when is it going to have issues? When cosine is 0. So what's cosine of pi over 2? 0. So what's going to be there for the tangent equation? I really want everybody with me. Isn't tangent sine divided by cosine? Won't I have to put a vertical asymptote whenever the bottom is 0? In this case, cosine. Isn't cosine 0 at pi over 2? Therefore, a wall goes here. And there will be another wall at negative pi over 2. So this is kind of crazy. It looks kind of cubishy. Just really kind of elongated in the middle. It's hard not to make tangent look like it's a straight line, but it's got to curve up towards the asymptotes at the ends, yes? But it is yeah, the slope of it's very strange. Is that the whole graph of tangent? No, because it's going to keep doing that same shit forever in both directions. Poor little guy. So how many asymptotes does the full graph of tangent have? Infinite number. For me, you only have to graph the middle portion. Does the idea of amplitude make direct sense here? Because amplitude's kind of like a ceiling and a floor. Does that make sense? But what does if I would have put a 2 here, what would have changed? Yeah, at pi over 4, it would have been 2. And it would have been negative 2. So there's kind of like, very often I'll put in quotes, I'll put find the amplitude. That's not an amplitude, but it tells you where that goes. So I want you to see how many steps do I take to get through this cycle graphically. There's a asymptote, then there's a location related to the amplitude in quotes, then there's the middle, then there's the other location, then there's another asymptote. How many steps? 4 steps, kick ass, same as before. Thank the gods. But what's different here is, what's the period? Pi. That's right. Awesome pi. Okay. So tangent and cotangent, it should not make, it should not be surprising that the graph looks very different. Because they're the 2 functions that are made up of 2 other trig functions. So of course they're going to be really kind of weird. What's going to be different about cotangent? What's on the bottom of cotangent? Careful. Sine. So where is a wall going to be? Where sine is 0. So where's kind of like the first wall? What's sine of 0? So there would be a wall here. Where's the next wall going to be? pi. Calm down, Jeff. So tangent lives between negative pi over 2 and pi over 2. Cotangent lives between 0 and pi. And again, what's the period of cotangent? Very obviously. Maybe not obviously. The period of cotangent. Pi. What's cotangent of pi over 2? Think about it for a second. Be careful, what's on the top of cotangent? Cosine. What's cosine of pi over 2? 0. What's sine of pi over 2? 1. So 0 over 1, 0. So you might think, is it going to be cubish again? Yes. But what's cotangent of pi over 4? Remember, the beautiful thing about sounding cotangent and tangent is there's some kind of 1 at 45-degree angles, correct? And pi divided by 4 is a 45-degree angle. So what's cotangent of pi over 4? 1, because that's where sine and cosine are equal to each other, right? So see how it's going to be. So cotangent of 3 pi over 4. What quadrant is that in? 3 pi over 4. Second. It's not quite a full pi, right? Not quite a full pi. Poor little dude. Second quadrant, what's true about sine and cosine? The sine, S-I-G-N. They're both different sides, correct? So of course cotangent is going to come out negative. So it looks just like tangent, except it's been flipped. So that's cotangent. Drawn absolutely wonderfully. No issues, no notes. Or I mean like a billion notes, that's what. But this will be perfectly fine with me. I need to see asymptotes, and then I need the shape of it, right? So then I can do all the same stuff we did for sine and cosine. I could move them around, I could shrink them, I could stretch them, all that kind of stuff. Okay. What sucks about tangent, where does it start? Where does it start? Negative pi over 2, yes? So remember when I said the begin and end cycle thing was optional for sine and cosine? It's not optional for, trust me, dear God. Trust me. If I try to do it without doing that, I gotta really, the beginning end cycle is huge for tangent. So let's do this. Let's do one tangent example, and then I'm gonna let you out. See if that focuses everybody. Did you say we can leave early? No, I don't know what you're talking about. Which pen am I using? Jesus. So let's say I've got 3 tangent of, sure, pi x minus pi. Sure, Jeff. So in quotes, I would ask you what the amplitude is. This is not really an amplitude, but it's still necessary, because that tells me where I am on the second and third steps. What's the quote amplitude? 3. If I factor this, what do I get inside? So what's k? K? Pi. So what's the new period? What's the old period? Pi. So what's the new period? So you always divide the original period by k. So don't get used, we got so used to 2 pi for sine and cosine because their period's 2 pi. Now in tangent, cotangent, those periods are pi. So my new period's 1. What's my step size? 1/4. New period divided by 4. Let's try begin and end. So if I take what it was, what do I set it equal to? Because where does tangent start? Careful. Negative pi over 2. And then it ends where? 5/2. That's what the normal tangent does. There's something we did earlier that would come in handy here. Kill the pie, right? I say eat the pie. Yummy. So then if I add 1, I get 1/2. I did forget my phase shift, but we'll be okay. We'll do that right now. What is the phase shift? Where do you look to see the phase shift? So what's the phase shift? Yeah, right 1. So I need you to see, where do we begin? 1/2. But didn't we go right 1? Okay, it's because tangent doesn't start at 0. So not only am I shifting it over, I'm also smushing it, aren't I? I need you to see what I'm saying. Aren't I smushing this? Because we changed the period. And I'm shifting it right 1. So that's why I don't get 1 for the beginning, because I smushed it also. It's really difficult to realize how those two things are going to go together. If you just do the begin work, though, it does it for you. If I do that, I see where I'm going to start. Trust me on this. So then I can kill the pie again, or, better eat it. And then I get 3/2. And does that do what it's supposed to do? What should the period be? How long should it take for it from the beginning to the end? 1. And sure enough, that's 1 apart, yes? Okay. Oh my God. Okay. So let's see if I can gather all. Everyone got all that stuff? Yay, Jeff, we love this shit. Okay. So I'm going to start at 1/2 and go to 3/2, yes? And my step size, what's my step size? Did I do that? Yeah, 1/4. So what I'm going to do then is I'm going to make this 2/4, and I'm going to make this, you can do it, Jeff, 6/4. Okay. So if I make this 2/4, no, Jeff. Goes better with my step size, because now I step by 1/4. So this will be 3/4, 4/4, 5/4, 6/4. So now my step size, if I apply my steps, I do end where I'm supposed to end. Does that make sense? If you make your step size and your beginning LCD, it's easier to go ahead and count. So tangent, what's at the beginning of tangent? And cotangent for that matter. What starts everything off? What is there? There's an asymptote there. And of course it ends at a wall also, yes? What happens in the middle? It's the middle. I love it. So the first step in, what's my amplitude, quotes? 3. So where should I be at 3/4? Good, -3. And of course at 5/4 I'll be at 3. And then I got to approach my walls. Try to put a little curve to it, yeah? It's not a straight line, even though it's it's one of the straightest curvy dudes ever. If this had been cotangent, well, a lot would have been different, to be honest, so I'm not even going to say it. A lot would have been different, because what would this have been if it would have been a cotangent? 0. And what would this be? Pi. So those are the things you have to memorize. The work is basically the same as before. I just have to be careful about what the new period is, for tangent, cotangent, where they start and end. That's different. Okay. Very exciting, Jeff. Thank you so much. Okay. So let's end early today. That sounds good to me, man. It's been a week and a half in a week. It's crazy. Everybody got a practice test, yes? Okay, so I have the key next Tuesday. Monday we got the quiz on all of chapter 7. And then we'll finish up chapter 8. Okay. Yeah. 8-2. We did 8-2 today. Oh, I forgot. Darn it. I'll give this to you. Ah, shoot, man. Here, guys. I'm sorry. I'm gonna email this out probably, but I want to give you this real quick.
You don't have to memorize the units.
Hell no. But I just give this for reference. I'll send an email out for everybody else. So it's on there. There we go. Dan, damn it, Jeff. Okay.
Handouts.